In this video, we introduce a new integration technique called integration by parts. Let's first examine a very typical, simple integral. Let's look at the integral. It's a product x times sine 3x. Normally, we would try to introduce some substitution to simplify this, so hopefully we can integrate it just like sine u if we assume 3x to be replaced by u, the substitution. But you check out if you differentiate the right side, you get a 3 dx. There's a leftover x that's not going to go away, and you try it out, it's not going to work. It's impossible to turn this into some integral in u. So substitution method works. As a matter of fact, there's just no substitution that's gonna work. There's nothing else you can try. Anyway, because of this and the other reason, we want to know other ways that we can use to evaluate integrals like this. The proof of the integration by part formula is actually pretty simple. Let's check out the product rule in differential. It's just a differential of a product u and v equals u dv and v du. So we are assuming in this identity u and v are two functions of x. Alright, now if we integrate both sides, integration cancels out the differentiation. So this is just u times v, or this is a u dv v du. And here comes our integration by parts formula. For example, we can move this term to this side. We have our u dv equal to uv minus v du. And this is our integration by parts formula. Now, when you look at the formula, it seems that you're going from some integral to a new integral. Well, the hope is with this transition, with this formula, the new integral is simpler, or better yet, integratable right away. Alright, so how do we apply this integration by parts formula? Well, given integral you see here, the left side you start out, there are two parts. The one part considers u, other part is dv. In order to apply the formula, you got to be able to determine your v. So you have u times v minus then the v du, so you can set up this integral. What it means is, for example, in this integral, you see the x, you see sine 3x, you see dx. You need to divide this whole product into two parts. One part is u, the rest is dv. Your dx always goes with the whatever you consider as dv. Alright? Now, when we try to apply this formula, there's one thing that we have to remember all the time. Whatever we consider as dV, we got to make sure it's first of all possible to determine the V. Say you consider dV equal to whatever. For example, in this old integral up here, you can say dV as x times dx, or you can say dV as sine 3x dx. So you can see here, your dx is always part of dV. Whichever way you decide, saying you got to make sure it's possible to determine V. That is, if you integrate both sides, you can do the integration. That's one criteria. Another criteria is, hopefully you determine your dV in such a way that your V will be simpler than whatever you start out here. Now let's check these two options. If we integrate, V would equal to 1/2 x squared. That's not preferable because you end up with a more complicated function. Well, here dV equal to sine 3x dx, you integrate, it will become negative 1/3 cosine 3x. Now that's not better, simpler than sine, but it's not worse. So sine, cosine, you go from sine to get cosine, or you go from cosine to sine, it's okay, not getting any worse. Alright, so if we can choose, we rather take this one, not this one. Alright, so it's very important how you decide your u part, the dv part. And in practice, what you do is to actually determine your u first. The rest will be dv. And how we determine the u, then the leftover for dv is we always pick up functions that are hard to integrate as u. Therefore, the leftover will go to the dv part, making it easier to integrate, possible to integrate. And the integration hopefully will give us no worse than the function we start out like this. Start with the sine, we get the cosine, that's not bad. Alright, so remember, in order to make this thing work out, we need to determine the u correctly, and that's very important in assuring that the new integral is at the least simpler than the old integral. Well, here I prepared a list of choices for you. Let me first read the list and then tie this to what I was explaining. So you want to choose your u following this order. Given integral, you look for log. Log is bad. So if you see log or power of log, automatically that's your u equal to log, and the rest will become dv. When you try to apply the formula. And the other bad guys, well, it depends. Just anything you think is hard to integrate, like an inverse sine, it's just impossible to integrate directly. There's no formula, there's just no clue, actually. Inverse secant and so on. Bad guys. All the bad guys. Now if you don't see any of those bad guys, look for power. Power is not so bad, it's not so good either. It's not so bad because we can actually integrate. It's not so good because we integrate, we get a higher order power. That's worse. Well, at least it's possible to integrate. So her last choice would be among those guys. Those are good guys. Think about this. If you have like a, yeah, this thing can go to be DUDV. So this will be the last choice for you, because this way they would become your choices for thing to include in your DV. That's easy to integrate. So the functions that are easy to integrate are the last choices for your U. If you don't have any of those bad guys, or even not so bad guy, well, you'll be left with all this thing anyway. So it doesn't even matter. So you're gonna call U equal to this or this or that. But that's your last choice, which basically says those will be your first choice to be included in your DV, because it's easy to integrate. It's easy to integrate this, and there's direct formula. This doesn't look nice, secant times tangent, but it's easy to integrate. So you choose your U following this order. So once you get those as one of those as your U, well, those guys would be part of your DV. That's easy to integrate. So bad guys. All right. Let's again before we start any concrete example, let's examine this x sine. So get this idea. Compare to sine x is worse. There's no log. So if we go by the list, there's a log, and we have power, first power, x is first power. So that's our choice for U. That's U, and these two would be dV. The sine will become part of dV. And you can imagine here, like I was saying, once you set the dV equal to sine x dx, you integrate, you get no worse function than the function you start out. So that's not so bad. All right, let's see examples. And the list, very important. So let's see, in this integral, x to the third power times log. Log, our first choice. So automatically U equal to log. That's it. This is U, therefore x to the third power and the dx will be dV. According to our formula, we're going to have U times V minus V du. So we need to find out the V. Integrate both sides here. So V equal to x to the third power dx. That's 1/4 x to the fourth power. Now we don't need a plus here. We just need a 1V. Okay. So we start with the U dV. Now let's write down U times V. U times V minus V du. Integral V du. V, we have to figure out. Du, well, from here, du is 1/x dx. Alright, so let's look at our new integral on the, well, it's not right, it's the new expression. We start with the product of power and the log. Now this is like a power times power. Well, you can actually simplify, so it's actually simple power. So this integral is obviously simpler than the original integral, and we simplify to see it is actually a very easy integral to evaluate. Now you need to combine first. The 1/4 you always pour out. The power here and this 1/x you simplify algebraically as well. Third power, very easy to integrate. And it's well, power 1/4 x to the 4th power plus c. Done. All right. When you apply integration by power formula, well, you always have like a v times du, so that's pretty much always a product. So that's what we got here, product. Whenever possible, you have to simplify. You cannot directly integrate this power, get 5th power, and integrate this to get the log. There's no such product rule. Again, don't make this kind of mistake. Okay, this is a very straightforward integration by parts formula, integration by parts problem. You have a combination of power and power of x and the log, so it's a no-brainer that you can take a log as you and proceed and apply formula. It's guaranteed you get a simpler integral. Turns out this is a new integral after simplification, so that's of course much simpler than the original one. Let's see another example. So here again is a very typical integration by parts formula problem. We have power of x exponential. So let's go by the list. Well, notice there's no really bad guys like a log, like an inverse trig, those ugly things, right? And then we check, well, there's a power, so we go down on the list to say there's a power, so that's our u. So u is x to 2nd power, and then the dv. You see, once we pick out the worst guy as u, the better guy will become part of the dv. Let's say if we integrate both sides here, simple substitution, very get half e to 2x. So you can see the expression v we obtained, right, is not really that much different than the function we start out. That's good. All right, so let's see, this is the integral start out u dv equal to, remember, u dv equal to u times v. So u times v minus v du. Well, what's du? It's 2x dx. Pretty simple. Product 2x dx. Now rewrite the first term, simplify the new integral, have to cancel each other, so it's basically e to 2x x dx. This new integral, first of all, is obviously simpler than the old one. Start with the square times exponential. Now it's a first power times exponential. We need to do integrating by parts again. So of course you cannot integrate the exponential and the x, right? That'd be wrong. There's no such product rule. Well, if there were, we would be able to start out right there, but cannot do that. Anyway, so this is the thing we're doing to turn the original integral to this new one. Now we're going to do a new integrated parts work again. So this part we don't have to worry about. Just copy it down. Let's focus on this time just this. Now what do we have? We have exponential versus power of x. X is the first power, so it's power of x. So again, we're going to take power as u equal to x, and the dv of course will be e to 2x dx. This as u, the rest will be dv. Now I'm using the same letters u and v. We're working on different integrals, so this u and this v are not the same as the uv before. Okay, you can pretty much forget about what we were doing. Okay, it's just a new work we're doing to try to evaluate this new integral. So integrate again. Just actually this happens to be the same as that integral, so we can just copy the answer. And the du equal to x, you know we need the du too, right? So du equal to dx. Now apply formula, integration by part formula. Okay, u dv equal to uv minus v du. So from this we have a u times v minus v du. Once again, you can see the new integral here is simpler than the one we started out. Before was a product, x times exponential. Now it's just exponential. This half is a constant being pour out. That's my level. We're going to just do that. Remove the brackets. Minus minus becomes plus. The half move up. So basically we have a very simple integral. Of course there's a substitution involved. We've done this a lot. You know, you can say u equal to 2x as a substitution and the work out. Oh, it's gone. So it's plus c. Expands. So basically this is just another very typical product that we integrate. We do integrating by parts. Now another thing you notice in this example is we had to use integrating by parts twice. That's not uncommon. Alright, each time we do what we can. In this case we apply integrating by parts and with a simpler integral, and that just says we were on the right track. And for the new integral, and then again we do whatever we have to. Turned out it happened to be just integrating by parts again. Okay. Let's see another integral. This is integral of inverse secant of square x. It's not a product. There's only just one thing here. There are a lot of integral like this. It's an integral of a bad guy, just one term. Well, in a way, it's pretty simple. If it's bad, I mean, there's no substitution, there's no formula, you know, we can apply. So now, obviously, we're going to try integrated by parts formula, and also it's kind of easy to decide because that's bad. It's bad. We just have to assume it to be the u. Well, since this is the only factor here, now that's u. The rest is just dx. So your dv is just dx. All right. The whole thing is considered as u. The leftover is just dx, and that's fine. Other problems, you may have a square of log, just 1 power. Well, again, you would assume your u to be square of log and dv equal to dx. Alright? Well, here, if you integrate, v is just x, dv is dx, v is x. That's kind of simple. You know we're going to need the du. So what's du? The derivative inverse secant is 1 over square x, square root of square x square minus 1 times 1 over 2 square x dx. It's a square x, and the square x multiplied is x. This square x squared is x minus 1. Looks bad. Anyway, let's just apply formula, see what we have. Doesn't look to be simple, but then when you check out everything we have that we're going to the new expression, they're simpler than inverse trig. Okay, so this was u dv. So now u times v. What's u? This is u. U times v minus v du. This is du. 1 over 2x square root of x minus 1 dx. Alright, this part we don't worry about it because it's done. We're doing integration. We don't need to worry about this at all. Just copy it down. What we need to check is this. What is this? Well, it's a fraction. Actually, it can be simplified. The x here and x here cancel out, and the 2 pour out. It turns out the new integral is a pretty simple one. You can do substitutions. Let's see. Simple substitution would work out. So let's say, suppose we say u equal to x minus 1, du equal to dx for substitution. Alright, of course not the same u we used to do the integrated parts in the beginning. So here the radical becomes a half power, so it's u raised to half power. Dx is du to the integrated power 1 over 1/2. Negative 1/2 plus 1/2. U raised to 1/2 plus c. Half cross out, u x minus 1 to half power plus c. Done. Alright. Now we got another example here. The main thing I wanted to show through this example is that there's only one part that you cannot apply formula to integrate, cannot do substitution to integrate. So integrate by parts, how do we do it? Even with one part, we can do it, but most often you just assume pretty much the whole integrand as u and try it out. Now finally, let's see integral. Fifth power times radical. It's a product. Now, say we go through the list. There's no really bad guys. What do we actually have? Power, obviously, and the radical isn't like a power. So this is one thing I want to really explain is when you have a combination of powers, both like from the second group, you never try integrating by parts. Integrating by parts will not work. If you have a combination of one function from this, one function from this, yes, pretty standard, typical integrating by parts problem. If you have a power and one of those guys, again, you do integrating by parts. Or maybe you have one from the first group, one from the last group, you do integrating by parts, but not both from the second group. Both from the third group, it's possible. All I can say is possible. Not both from this group. Never both from this group, because even one is bad. Two together, it's pretty much impossible. Anyway, this is the integral that contains actually two parts. From that, no hope for integrating by parts. So we just have to try something else. What else? Well, the only other technique we know is substitution. Even though initial check with the concept of supporting factor, substitution will probably not work, because if you differentiate this thing, you see 3 times x squared. You expect the x squared perfect supporting factor in place is x to the 5th. So it's, well, looks like it would not work. There's no other choice. We'll just give it a try. Remember before, sometimes even there's no perfect supporting factor in place, it would still work out. Well, actually, this is the case too. Let's see, the substitution, u equal to x to the third power plus 1, this will become square u. Du is 3x squared dx. Let's see. With this substitution, this part becomes square u. Nice. Now, normally, in perfect situation, we would have x squared here, and it's just very easy, very simple, new integral. Well, not this time. This time we have x to the 5th. So with the differential identity, we can get rid of 2 copies of x. So let's split this as the third power and the second power. So the second power will go with the dx. That's gonna give me 1/3 du. It says here square x and the dx becomes 1/3 du. There's still third power. Well, it's actually not bad. Third power, according to this, is u minus 1. You move 1 over. So of course, it was not the perfect power for x to the 5th power to be supporting factor. It's not so bad power. It's just kind of special, but we actually can still make things work out with this substitution. Well, you can see from here on, just multiply through. This is half power, or 1/3 move out first. this 1/2 power, 1/2 power, first power, so we have U2 3/2, U2 half. It's important it's a third power because we can still use substitution to get not so complicated expression in place for x to the third power. If you think about this, as long as the leftover is power of x to the third power would work. Okay, so you can imagine if it was a 7th power to start out, it would still work. 7th power. No, I'm sorry, not 7th power, 8th power. 8th power would still work out because you take a square to go with that, you'll be left with a 6. 6 is the square of that, so you would have square of this. Alright, 5 would work, 8 would work, 11 would work, so on. Same idea. Once you take away square that you would need, to get 1/3 du in, the rest, as long as it's a multiple of 3, it would work. Anyway, so we integrate simple powers. So 1/3/2 plus 1 u 5/2. 1/2 plus 1 u 3/2 plus c. And simplification, simple simplification. This is like 2/5 u 5/2, 3/2, or 2/3 flip. Alright, so this last integral shows that an exception. Okay, have both parts as powers from this group. You don't do integrating the parts. If you're curious, you can try. You can try, hey, this is u is dv, or this is u is dv. It's guaranteed you're gonna get a much worse integral. On the right hand side, once you apply integrating by part formula. Alright, so this is another integration technique, integrating by parts. The key is to choose your u correctly. Most of the time, follow this order. Okay, look for u. See if you have any of this guy. If you do, that's your u. If you don't see any of this, look for parallax. Alright, if you don't see this, you would see those. Then it doesn't really matter which one you want to pick up as your u or dv.